Hello there. So let's take a look at chapter 5, taking us to the halfway point in the semester. Yay! And looking at chemical reactions in chapter 5. So as we normally do, we'll start with a couple of scenarios. So one of your patients is taking vitamin B12 to ward off pernicious anemia. However, she's worried that it's a very small amount because the dosage is in micrograms, while the vitamin C tablets she takes every day are in milligrams. How could you reassure her that she's getting the same good dose of vitamin B12 in her diet as she is vitamin C? Well, different chemicals have different masses, like different people have different masses. So 5 pounds weight loss for one person isn't the same or as drastic as 5 pounds weight loss for someone else. If you weigh 140 pounds, 5 pounds weight loss is quite a lot. If you weighed 300 pounds, then 5 pounds isn't such a big weight loss. So it depends on how much of that thing you have. And it's the same with chemicals. How much of that chemical do you have? And we measure those chemicals in molar amounts, and we'll talk about those. And that's the best comparison you can make, molar amounts of chemicals. Talking to a patient who's being fitted with a new pacemaker, and they're worried about the reliability of the technology. That isn't such a big issue now, but it used to be. He says he wished he knew how the pacemaker worked. Would you be able to tell them how that pacemaker worked and to describe the chemical reaction which takes place at the heart of every pacemaker? So to begin with, we had talked very briefly in chapter 1 about the conservation of mass in chemical reactions. The total mass that went into the reaction came back out of the reaction. And we will talk about that more in this chapter and take it chemical by chemical and work out how much of each chemical we should have and produce. But of course that uses equations which are already balanced, with each element appearing the same number of times on both sides of the equation. So we've got the sodium hydrogen carbonate there. There's one atom of sodium in each molecule, and we're starting with 2 molecules to give us 2 sodiums. So there must be 2 atoms of sodium that come out of the reaction. And we can see that with the sodium carbonate produced. There's 1 atom of hydrogen in each molecule of sodium hydrogen carbonate. And with 2 molecules, we've got 2 atoms of hydrogen. Likewise, 2 atoms of hydrogen making up the molecule of water that's produced. So for each element that's being used, we see that element being produced out of the chemical reaction, maybe having new partners as we make new chemicals, but the same exact amount is coming out. And so we quite often have to balance equations to get to this point. We've got the same amount of chemical on both sides of the equation. Now it's just a couple of simple rules we can use to perform this trick. First and foremost, just identify any element which is unbalanced. Those are the ones that we'll focus on as we try and balance up the reaction. If you see an element which is part of its own unique chemical formula, then leave that last to balance. And what we mean by that is, if I get my annotation tools, let's move them up to the same page I'm looking at. So elements in their own chemical formula, that would be something like nitrogen gas. There's only nitrogen in nitrogen gas, or maybe something like oxygen gas. We only have oxygen atoms in oxygen gas. Or it could be an element like zinc, which just stands alone in its own chemical formula. These kinds of chemicals, when seen, these give us elements which could be left last to balance, because then when we do balance those, we don't affect anything else. If you're trying to balance something like maybe carbon and methane gas by taking 3 times as much methane, you can't treble the amount of carbon without trebling the amount of hydrogen in the equation as well. So we always want to have, if possible, an element which is part of its own unique chemical formula when balancing things to finish off the reaction. So start by balancing elements from left to right, one element at a time. And if you can, it's good to start with elements which appear just once in the equation on each side. Makes them a little bit easier to balance. But just bear in mind, you won't always have that luxury. When you are balancing for the element, just keep in mind that you're only changing the coefficients at the beginning of the chemical formula. You're not actually changing the chemical formula itself. So if we have carbon dioxide in a reaction and we needed to double the amount of carbon, we'd have to double the amount of carbon dioxide if that was our source, but we just change the number, the coefficient in front. So we'd take 2 units of carbon dioxide. We don't suddenly change to C2O4. That's a completely different formula and therefore a completely different chemical. You do not balance the equation by changing the reality of the chemicals which are used up or the chemicals which are produced in the reaction. But as always, let's look at a couple of examples to clear this up. So if we had taken an equation with nitrogen and bromine, and they're producing NBr3 nitrogen tribromide. With these examples, you'll always be able to assume that the chemical formulas themselves are actually correct. So nitrogen tribromide is the correct formula, NBr3. Now we can break it down by element and see how much of each element we have in the equation. One sec. One sec. Somebody needs a drink. Hang on. All right. Okay, apple juice supply. That should keep her busy. Okay, so we're only changing the coefficients, the numbers in front of the chemical formula. So for example here, we've got 2 atoms of nitrogen going into the reaction, but there's only one atom of nitrogen in that molecule of NBr3 coming out. For the bromine, there's 2 atoms of bromine in the bromine liquid, but there's 3 atoms of bromine coming out of the reaction. So we need to balance, and I've just chosen to balance nitrogen first. At some point, you'll just have to make a choice between the elements you're balancing. Just take them one at a time. So with 2 nitrogens on the left, but only 1 on the right, we need to double the amount of nitrogen that's on the right. And we do that by taking 2 molecules of the nitrogen tribromide. Now, of course, that's going to double the amount of bromine that's on the right as well. So instead of 3 atoms of bromine from that 1 molecule, 2 times that the 3, we've got a total of 6. So nitrogen's balanced, 2 and 2. To balance the bromine, which is now a 2 to 6 ratio, we need 6 atoms of bromine on both sides. You're either trying to pitch towards the higher of the 2 totals or the smaller of the 2 totals. Usually, you're trying to get everybody up to the higher total. So 2 times something to make 6, that would be 3 times more. And so we take 3 molecules of the bromine. It gives us our final balanced equation. 1 molecule of nitrogen, 3 molecules of bromine, and it produces 2 molecules of the NBr3 nitrogen tribromide. Any questions about that one? We're doing okay? So 1 element at a time. And keep balancing until everything is balanced. And if you see an element which is part of its own unique chemical formula, that's usually a good thing to leave till last. And we take a look at the next one. We've got aluminium reacting with iron oxide, Fe3O4, and it's producing aluminium oxide and iron. So again, we can break it down element by element on the left and the right-hand side of the equation, as we do here. You don't have to do all this, but it's something I do just for teaching methods. There's 1 atom of aluminium, 3 of iron, 4 of oxygen, compared to the end of the reaction, which contains 2 atoms of aluminium, 3 of the oxygen, and then 1 of the iron. So looking for something to balance last, we could choose either aluminium or iron, because they do appear in the chemical equation in their own chemical formula at one point. So that means that we should really be balancing the oxygen first. We've got a ratio of 4 to 3. We want the 2 sides to be equal. So looking for a common denominator between them, 4 and 3, lowest common denominator would be 12. So 4 times something to make 12, that would be 3 times more, to give us 3 molecules of the iron oxide. 3 atoms of oxygen on the right times something to make 12, that would be 4 times to make 12. So that gives us 12 atoms of oxygen on each side. Now, of course, that trebles the amount of iron in iron oxide if we take 3 molecules. So we update our iron total, taking 4 molecules of aluminium oxide, or 4 units. That's quadrupling the amount of aluminium. So instead of 2 units, we've got 4 times more, 8. Always keep track of how other chemicals or other elements are affected when you change the coefficient for your chemical formulas. So with the oxygen balance, 12 to 12, it's a 1 to 8 ratio for the aluminium. So we'll take 8 times more aluminium on the left, giving us 8 units. The iron, that's a 9 to 1 ratio. So we need 9 times more iron on the right. So we'll take 9 units of the iron. And it gives us our final balanced equation. It's very common for that final answer, the coefficients in that final answer, to be just single-digit numbers. We do occasionally get into bigger values, but if you're getting into 30s, 40s, 50s for the number of molecules, that's probably a good sign that something's gone wrong. Occasionally hit the teens or the 20s, but most of the time we should just have single digits for certainly the majority of the chemicals in that final balanced equation. All right, let's try another. This time with the oxidation, the combustion of some butane, C4H10. So again, you're given the raw equation at the top, and we'll look at each element as it appears. Carbon, 4 carbons on the left in the C4H10, 1 carbon on the right in the carbon dioxide. For hydrogen, we've got 10 on the left in butane, but only 2 atoms on the right in water. And then for the oxygen itself, a little bit more tricky because we've got multiple sources of oxygen. On the right-hand side, it's part of carbon dioxide and the water which is being produced. So with oxygen in its own formula on the left-hand side, oxygen gas, that's a good thing to leave till last. So it gives us a 50-50 chance of either balancing the carbon or balancing the hydrogen. As I read the equation from left to right, I just like to balance elements from left to right. So I'll balance the carbon first. 4 carbons on the left compared to just 1 carbon on the right. So we need 4 times more carbon on the right. So we'll use 4 molecules of carbon dioxide. That quadruples up some of the oxygen. So instead of 2 atoms from 1 molecule, we've got 8 atoms from 4 molecules, plus the 1 atom of oxygen from the molecule of water. If you've got multiple sources for the same element on each side of the equation, it's sometimes useful to keep track of those individual sources as well as the total amount of the element on that side of the equation. So we've balanced the carbon, that's now 4 to 4 as we want. I'll take the hydrogen next. We've now got 10 compared to just 2. To get the same amount of hydrogen on both sides, we need 5 times more on the right. So we'll use 5 molecules of water, 5 H2O. That also has an effect in the amount of oxygen. Instead of 1 atom in the 1 molecule, we've got 5 atoms in 5 molecules. So our oxygen total on the right, 8 plus 5 now comes to 13 compared to the 2 on the left from oxygen gas. So for the balancing of that oxygen gas, a number that fits both 2 and 13, so we need something times 2 to give us 13. That would be 6.5 units, or 6.5. So it does balance our oxygen. 2 times 6.5, that's the 13, just like the total of 13 atoms on the right. But we never leave an equation with any fractions or decimal places. So as a final step, we just multiply out that fraction, multiply by the 2. So twice as much butane, that would be 2 molecules. Twice as much oxygen, that would be 13 molecules. Twice as much carbon dioxide, that would be 8 molecules. And twice as much water, that would be 10 molecules. Quick check, none of our numbers, our coefficients, can't all be divided by a smaller number to still give a whole numbered answer. That's the important part. It's the lowest whole numbered ratio for the equation. Then that makes sure that everybody else uses the exact same equation. Any questions about that one? I think in the Chapter 5 folder there is a video for some of these examples, so you can look at those too. I also, on Desire to Learn this morning, put up the Chem Talk video for balancing equations, which has other examples. Looking at the next one, a little bit trickier still, because oxygen is part of every single chemical compound in the reaction. So that's definitely something we want to leave last, especially with oxygen forming its own formula. That could allow us to adjust the amount of oxygen here without affecting anything else. So we'll take it from left to right again. 7 carbons on the left, but just 1 carbon on the right. So we'll multiply our carbon content on the right by 7, giving us 7 molecules of carbon dioxide. That also adds a huge chunk of extra oxygen, 7 times 2, now 14 oxygens, together with that 1 hydrogen from that 1 oxygen from a molecule of water. That gives us a total oxygen count of 15 to handle later. Now that we've balanced the carbon, the hydrogen count, that's 6 compared to just 2. We want both sides to match, so we need 3 times more hydrogen on the right. So we'll take 3 molecules of the source, 3 molecules of water, which of course also has a multiplying effect on the amount of oxygen. So the 14 plus 3 now gives us 17. But we've now balanced the carbon, now balanced the hydrogen, we just have the oxygen left. Now we'd like our total oxygen on both sides to match that higher total of 17. But remember, we've got 2 sources of oxygen on the left. The only one that we want to affect is the one which doesn't affect any other element in the reaction, the oxygen gas. So we want a total of 17. We already have 2 oxygens from the heptanoic acid, which has been described here. What is it, heptanoic? No, it must be a benzene derivative with just that number of hydrogens. So we've already got 2 oxygens here. So this oxygen source only needs to amount to 15 together with 2 to give the 17 we're looking for. So 2 times something to make 15. That would be 7.5 or 7.5. We put that in as a coefficient, and the oxygen now balances on both sides without affecting hydrogen or carbon. But it does leave us with this nasty fraction, this decimal place in our answer. And remember, we don't allow for fractions, decimal places in the final answer. So our usual trick of just doubling through by 2 to get rid of that decimal place. So instead of 1 molecule, we have 2. Instead of 7.5, we've got double, 15. Instead of 7, we've got 14. Instead of 3, we've got 6. We can't leave that fraction, that decimal place in a final answer, so everything gets doubled up, because this is a balanced equation at this point. Next one, with the P4O10 tetraphosphorus decaoxide. That's reacting in water to produce H3PO4, phosphoric acid as it's known. Now this one, oxygen, is again tricky because it's in every chemical formula. So let's leave that last. We start with the phosphorus. We've got 4 atoms on the left, but only 1 on the right. So let's have 4 times more phosphorus on the right with 4 molecules of the phosphoric acid. That also has a trebling effect on the hydrogen and the oxygen content. So now 12 and 16 in total on the right. We look at the relative hydrogen amounts. There's just 2 hydrogens on the left compared to 3 times 4, 12 hydrogens on the right. And so to balance the two sides and give us 12 hydrogens on both sides, 2 times 6 will balance the hydrogen. And that's also very nicely balanced up the oxygen, which we're going to tackle next. So 10 oxygens plus the 1 times 6, 16, equal to the 16 oxygens on the right, 4 in each molecule, 4 molecules, 4 times more, 16. So sometimes that last element will actually balance for itself once we have taken care of everybody else. Okay, oh, excuse me. I'm even boring myself today. That must be a record. Kind of dry doing balancing equations, but the nice thing is that once you've seen a few, it usually clicks, and then it's some easy marks for a Chapter 5 assignment. Any questions at this point on any of the ones we've done so far? Making sense? Nope. Somebody's taking a shower while they listen to the chemistry. That's a new one. Right. Next one, iron sulfide, FeS2. That's reacting with oxygen. What we sometimes call a combustion reaction. That's producing iron oxide, Fe2O3, and sulfur dioxide, SO2. We'll take it one element at a time again. We've got one iron, but 2 on the right. 2 sulfurs, but only 1 on the right. 2 oxygens, but 3 plus 2, 5 on the right. And again, we'll leave oxygen last because it's part of its own formula. So I just happened to choose to balance the iron first. It could just as easily have been the sulfur. So 1 iron on the left, 2 on the right. We double up the amount of iron on the left by using 2 units of the iron sulfide. That also doubles the amount of sulfur. So that's now a 4:1 ratio on the two sides. So we need 4 times more sulfur on the right, 4 molecules of sulfur dioxide to balance the sulfur. That also has a quadrupling effect on the amount of oxygen in the sulfur dioxide, 4 molecules instead of 1. So as we try and balance the oxygen, our targets are now 2 compared to 11. We want both sides to be equal to 11. So something times 2 to make 11, that's 5.5 or 5.5. That balances the equation. But again, we don't leave that fraction in the final answer, that decimal place. So with a half, easiest thing to grind it out is just multiply by 2. So everything is doubled at this point. The equation is balanced. So if you're going to double one of the ingredients, you've got to double everything to keep it balanced. So instead of 2 units, we've got 4. Instead of 5.5, we've got 11. Instead of producing 1 molecule of iron oxide, we're producing 2 units. Instead of producing 4 units of sulfur dioxide, we are producing 8 units of sulfur dioxide. Everything is doubled up to keep the equation balanced at this point. There's a couple of examples. Let's see how we're doing at this point. These are actually 2 examples from old exams, which people complained at the time were really tricky. I kind of agreed with them, so I actually took them out of the exam process. So these are good ones to practice. Try these and we'll take a look at the answers in a couple of minutes. Let's make it a break for the morning. So we'll look at these in about 5 minutes. And I will check and see how my rascally children are doing. All right, we're back. So let's take a look at those 2 examples for balancing equations. Let's see. give myself a bit more room here. And maybe increase the font size a little bit as well. Right. Okay, for the first one, it's probably a good idea to leave the oxygen last because it's part of its own unique chemical formula. We could affect the amount of oxygen here without affecting the amount of nitrogen. So as we look at the nitrogen on the two sides, it's 1 compared to 2 atoms of nitrogen. So we want to double the amount of nitrogen on the left. And so as we look at the amount of oxygen we have, we've got 2 in nitrogen dioxide, but there's 2 molecules. That gives us 4 oxygens, plus of course the 2 in the O2, which therefore gives us a total of 6. Compared to the right-hand side, we've just got those 5 solitary atoms in that one molecule of the dinitrogen pentoxide. So we're almost there, it seems. We're just out by 1 atom of oxygen. And we want to affect this source. But we've actually got the greater total on the left-hand side already. We can still use this. Instead of trying to get to the higher total, we can aspire to get to the smaller of the two totals by taking half a unit. 2 times a half gives us just 1. So the 4 plus the 1 would give us 5, as we have on the right-hand side. So normally you're looking for the higher of the two totals to be the thing you're trying to match, but sometimes it is a lower total by taking a fraction of a molecule, because we know that we don't use fractions in our final answer. And so to get rid of that half or 0.5, just multiply the whole thing through by 2. So we'll take 4 molecules of the nitrogen dioxide with 1 molecule of oxygen gas to produce double 2 molecules of the dinitrogen pentoxide. I think looking for the smaller of the two totals, 5 instead of 6, is one of the things that really caught people out with that one when it appeared in an exam about 6 or 7 years ago now, I think. Let's take a look at the next one. Let me clear up my work here. Okay. So if we look at the others. So we have got a lot of these elements appearing multiple times in the equation. Sodium appears twice on the left, it appears twice on the right. That's going to make things tricky. Nitrogen appears twice on the left and appears twice on the right in sodium azide and also in ammonia. And the only thing which appears exactly once on the two sides is oxygen, once on the left and once on the right. That's a great place to start. One sec. Right, we had a slight accident there. She bumped her chin, but she's doing good. She's a good girl. Right, so the oxygen appears exactly once on each side. That's a good in into this problem. There's 3 oxygens on the left, but there's only 1 on the right. We want them both to be the same, so we'll take 3 molecules of the NaOH, the sodium hydroxide. That balances up the oxygen. And then we have to lock in these 2 proportions. For every 1 unit of this chemical, there has to be, for all time, 3 units of this chemical. It's the only way to balance up the oxygen in this reaction. Now, unfortunately, there's no other element which appears exactly once on each side, but we do get a little bit of a break with hydrogen, which at least appears only once on the left and just twice on the right. But we've already locked in the hydrogen in the sodium hydroxide so that it balances the oxygen. You want to go? Okay, I'll be finished soon, baby. So with the hydrogen here locked in, that should hopefully mean that we only have to affect the hydrogen in this source. So let's see how much we've got. We have got 2 atoms of hydrogen here on the left. On the right hand side, 3 times 1, 3, plus the 3 from the ammonia. So that gives us a grand total of 6. So we want the total hydrogen on both sides to be 6. And so nice and easy, 3 times more. So we'll take 3 molecules of the sodium amide, NaNH2. That balances up the whole equation. 3 plus 1, 4 atoms of sodium. 1 plus 3, 4 atoms of sodium. 3 plus 1, 4 atoms of nitrogen. 3 plus 1, 4 atoms of nitrogen. That is our final balanced equation. 3 to 1 to 1 to 3 to 1 for the final proportions. Let's see. Let's look at a couple of ion chemistry ones just to quickly finish off. So with ionic equations, of course, we're dealing with metal and non-metal containing compounds. These can sometimes be tricky because of the polyatomic ions that we sometimes see in the formula. Things like NO3, nitrate. If that polyatomic ion appears on both sides of the equation, treat it like a unit, as if it was actually an element, and balance those nitrate ions on each side rather than individual atoms of those elements, nitrogen and oxygen. So polyatomic ions which appear on both sides can be treated like a unit. So if we look at our equation here, we have got 1 ion of mercury on each side. We have got 2 nitrates on the left, but only 1 on the right. We have got 1 atom of lithium, or ion of lithium on the left, and 1 on the right. 1 ion of iodide on the left, but 2 of them on the right. So it looks like there's 2 elements that we need to balance at this point. Let's start with the nitrate, 2 to 1. So we need twice as much nitrate on the right. So we'll take 2 units of lithium nitrate. That also doubles up the amount of lithium on the right hand side. So let's balance that next, a 1 to 2 ratio. So we need twice as much lithium on the left. We're going to take 2 units of lithium iodide, which also doubles up the amount of iodide itself. But that now balances. That was one of the elements we were looking at balancing, and now everything is balanced. 1 atom of mercury on each side, but 2 units of nitrate, lithium, and iodide, with that 1 to 2 to 2 to 1 proportions. Very quiet, very civilized as ever. Let's try one more problem, and that finishes off the ion chemistry bit. And we go into classes of reaction and climate change on Wednesday. If I had to guess, I would say probably we'll be online on Wednesday. I do apologize. But we'll be done with this silliness next week when we get back to the 2 days on campus for lecture schedule. So we'll look at this one. We've got aluminium nitrate. And we can see nitrate in the final proportions of the reaction with sodium nitrate. So we can treat that nitrate as a unit. We also have sodium carbonate with carbonate, a polyatomic ion. We see that carbonate at the end and aluminium carbonate. So we can treat the carbonates as units as well. So let's see, it looks like just about everything needs balanced, but I'll start from the left and move on to the right. So aluminium, there's 1 ion of aluminium on the left, but there's clearly 2 on the right. So I'm going to double up my aluminium by using 2 units of aluminium nitrate. If I take the nitrate next, now look, there's 3 of those nitrate units within every unit of aluminium nitrate. So 2 units, that doubles up to being 6. There's only 1 nitrate on the right-hand side. We want it to be 6 like we have on the left. So we'll take 6 units of the sodium nitrate. That has an effect on the sodium as well. We've got 6 times more sodium on the right, 6 in all. On the left is only 2. We want both sides to be 6. So 2 times something to make 6, that would be 3. So we'll take 3 units of sodium carbonate. We now have 3 units of the carbonate. But that's all right because there's 3 units of the carbonate on the right. And we've actually balanced the whole equation. 2 aluminiums, 2 aluminiums, 2 times 3, 6 nitrates, 6 times 1, 6 nitrates, 2 times 3, 6 sodiums, 6 sodiums, and then 3 times 1 unit, 3 carbonates, and there's 3 carbonates on the right-hand side as well. So again, we get our final balanced equation. Any questions before we finish for the morning? We've hit our target really of balancing equations. Remember, there is a Chem Talk video already up if you're thirsty for extra examples. And balancing equations plays a big part of the chapter 7, or rather experiment 7 today, which is based on chapter 5, the chapter we've just started. It's one of the more fun ones, the experiment today. We've got a couple of bangs in there as we burn hydrogen and oxygen and things like that. Okay, everybody doing good? Usually the balancing equations bit goes over pretty well, so I can't say I'm surprised. Okay, I'll see everybody at 2 o'clock. Stay safe, wash your hands, wear that mask.